Hi, and welcome to Mike Likes Robots, where we share knowledge to accelerate robotics. And today I'm going to show you my solution for day 22 of Advent of Code in Rust, called Monkey Market. This was a pretty satisfying one, not too difficult to do. I don't think I got the smartest solution, but given how fast it runs in the end, I didn't feel the need to improve it. So let's take a read through the puzzle part 1, then I'll show you the solution part 1, and then we'll repeat that for part 2. Day 22, Monkey Market. As you're all teleported deep into the jungle, a monkey steals the historian's device. You'll need to get it back while the historians are looking for the chief. The monkey that stole the device seems willing to trade for it, but only in an exchange for an absurd number of bananas. Your only option is to buy bananas on the monkey exchange market. You aren't sure how the monkey exchange market works, but one of the historians senses trouble and comes over to help. Apparently they've been studying these monkeys for a while and have deciphered their secrets. Today, the market is full of monkeys buying good hiding spots. Fortunately, because of the time you recently spent in this jungle, you know lots of good hiding spots you can sell. If you sell enough hiding spots, you should be able to get enough bananas to buy the device back. On the market, the buyers seem to use random prices, but the prices are actually only pseudo-random. If you know the secret of how they pick their prices, you can wait for the perfect time to sell. The part about secrets is literal, the historian explains. Each buyer produces a pseudo-random sequence of secret numbers where each secret is derived from the previous. In particular, each buyer's secret number evolves into the next secret number in the sequence via the following process. Calculate the result of multiplying the secret number by 64. Then mix this result into the secret number. Finally, prune the secret number. Divide by 32. Mix the secret number and prune. Multiply the secret number by 2048. Mix the result and prune. Each step of the process involves mixing and pruning. To mix a value, calculate the bitwise XOR of the given value and the secret number. Then the secret number becomes the result of that operation. If the secret number is 42 and you were to mix 15 in, the secret number would become 37. To prune the secret number, calculate the value of the secret number modulo this number, 16 million. Then the secret number becomes the result of that operation. If the secret number is 100 million and you were to prune it, it would become 16,113,920. After this process completes, the buyer is left with the next secret number in the sequence. The buyer can repeat this process as many times as necessary to produce more secret numbers. So if a buyer had a secret number of 123, that buyer's next 10 secret numbers would be, and it gives the list here. Each buyer uses their own secret number when choosing their price, so it's important to be able to predict the sequence of secret numbers for each buyer. Fortunately, the historian's research has uncovered the initial secret number of each buyer, which is your puzzle input. For example, 1, 10, 100, and 2024. This list describes the initial secret number of 4 different secret hiding spot buyers on the monkey exchange market. If you can simulate secret numbers from each buyer, you'll be able to predict all of their future prices. In a single day, buyers each have time to generate 2,000 new secret numbers. In this example, for each buyer, their initial secret number and the 2,000th new secret number they would generate are, and it gives the numbers here. Adding up the 2,000th new secret number for each buyer produces 373,27623. For each buyer, simulate the creation of 2,000 new secret numbers. What is the sum of the 2,000th secret number generated by each buyer? Your puzzle answer was, and there's my answer from when I did it. So it's quite interesting that there's a cycle of numbers. It seems fairly simple on the surface, and when I wrote it, at least part 1 was fairly simple. So let's switch over to the code and I'll explain what I did, where I went wrong, and how I got to my solution. Okay, so for this puzzle, I didn't end up using a struct, which I've used for essentially every puzzle since day 2, but I just didn't feel like there was anything I needed to store in a struct. So everything in here is just free functions. I defined a function to determine the next secret from the previous secret, defined the denominator as a constant above the functions, And then the actual calculation here is pretty simple. What we can do is take this set of numbers, or this set of text, copy it into here, and then you can see the first is to multiply the secret number by 64, which is the same as bit shifting left by 6. Then mix the result into the secret number, which is this XOR operation. Finally, prune the secret number, which is this modulo by the denominator. So one step of the mixing can be done pretty easily in one command. This is similar, except it's division, so we're bit shifting right by 5. Then again, XOR and modulo. Finally, multiply by 2048, which again is a bit shift left by a particular number, modulo by denominator, except this time I don't save the result in a variable, I just directly return it. So pretty simple there, except that I did get this function wrong. Initially, I only wrote the first line of the mixing algorithm, or the next secret algorithm. I only wrote this current left shift 6. And for a while, I was debugging and using tests to try and figure out why I wasn't getting the right numbers, why they didn't match what the puzzle gave me. That's probably the most time I spent on this puzzle, was figuring out why I didn't get my next secret function right. Just goes to show you need to read the instructions carefully instead of skimming over and starting coding. One other thing to mention, which I didn't add initially, but I added later as I realized I'd need to be passing more of these around, is a diff key. That will come in useful in part 2, so I'm going to leave the explanation for then. As well as the make diffs dict function, that's also for part 2. So here we are, secret after n. That's the part 1 function. And I just wrote this using a pretty simple iterator. I wrote a range from 0 up to, but not including 2000, so that 2000 times it will calculate the next number. Then it does a fold where it starts with 0 and the secret. And basically what happens is it's summing all of the secrets as it goes. So I think there should be secret sum after n technically. Okay, having rewritten that, I can see that the accumulator and the summing did absolutely nothing, so I'm going to remove that. So actually, this function is from 0 to 2000. Take the secret from the previous folder operation, apply the next secret function, and return that as the new accumulator. And then once the fold is complete, it returns that final secret. And you can see from these 2 runs that it ends up being the same value. So then my part A function is pretty simple. My main function being read the puzzle in and pass it to the part A function, so pretty simple. Part A is you read in the secrets from the input text. You use the lines, map each line to pass it to an integer value and then collect that into a vector. Or rather, a result which could be a vector and it could be a pass-in error, which I can then do a question mark on, which I do in the next line here. But essentially that means if any of the numbers in the text file fail to pass to an integer, it returns at this point with a result. Then it iterates over those numbers and maps it to the secret after 2000 iterations, which is n. N being the number. So yeah, the 2000 is hard-coded in here. I thought for a moment then it was passing in the 2000, but it's not. So does the secret after 2000 iterations given the secret n, which is why it's a misleading function name, and then does a sum across. So nothing too complicated here, and this did work out and calculated very quickly. So I've got a test text for it, and I've got a few extra test functions where I was trying to debug why my secret number generation wasn't working. So I took the secret numbers from the sequence in the puzzle. So if it starts with 1, 2, 3, these are the next numbers, and I check that that is true. It keeps calculating the next secret and asserting that it's the right entry in the map, in the vector. We've also got tests starting from 1 because that was the example. So you can see a lot of test functions for a fairly simple piece of code because I didn't get that next secret function right. But that is part 1, calculating successfully. Let's take a look at part 2. Of course, the secret numbers aren't the prices each buyer is offering. That would be ridiculous. Instead, the prices the buyer offers are just the ones digit of each of their secret numbers. So if a buyer starts with a secret number of 123, that buyer's first 10 prices would be 3 from 123, 0 from ending in 0, 6 from ending in 6, and so on. This price is the number of bananas that buyer is offering in exchange for your information about a new hiding spot. However, you still don't speak monkey, so you can't negotiate with the buyers directly. The historian speaks a little, but not enough to negotiate. Instead, he can ask another monkey to negotiate on your behalf. Unfortunately, the monkey only knows how to decide when to sell by looking at the changes in price. Specifically, the monkey will only look for a specific sequence of 4 consecutive changes in price, then immediately sell when it sees that sequence. So, if a buyer starts with a secret number of 123, that buyer's first 10 secret numbers, prices, and associated changes would be, and here they are listed here, and the important part here is the change, -3, 6, -1, -1. Note that the first price has no associated change because there was no previous price to compare it with. In this short example, within just these first few prices, the highest price will be 6, so it would be nice to give the monkey instructions that would make it sell at that time. The first 6 occurs after only 2 changes, so there's no way to instruct the monkey to sell then, but the second 6 occurs after the changes -1, -1, 0, 2. So if you gave the monkey that sequence of changes, it would wait until the first time it sees that sequence, and then immediately sell your hiding spot information at the current price, winning you 6 bananas. Each buyer only wants to buy 1 hiding spot, so after the hiding spot is sold, the monkey will move on to the next buyer. If the monkey never hears that sequence of price changes from a buyer, the monkey will never sell and will instead just move on to the next buyer. Worse, you can only give the monkey a single sequence of 4 price changes to look for. You can't change the sequence between buyers. You're going to need as many bananas as possible, so you'll need to determine which sequence of 4 price changes will cause the monkey to get you the most bananas overall. Each buyer is going to generate 2,000 secret numbers after their initial secret number, so for each buyer you'll have 2,000 price changes in which your sequence can occur. Suppose the initial secret number of each buyer is 1, 2, 3, and 2024. There are many sequences of 4 price changes that you can tell the monkey, but for these 4 buyers, the sequence that will get you the most bananas is -2, 1, -1, 3. Using that sequence, the monkey will make the following sales. For the buyer with an initial secret number of 1, those changes first occur when the price is 7. With initial 2, they occur when the price is 7. With the initial 3, it doesn't occur within the 2,000 changes, the first 2,000 changes. For the buyer starting with 2024, that set first occurs when the price is 9. So, by asking the monkey to sell the first time each buyer's prices go down 2, then up 1, then down 1, then up 3, you would get 23, 7 plus 7 plus 9 bananas. Figure out the best sequence to tell the monkey so that by looking for that same sequence of changes in every buyer's future prices, you get the most bananas in total. What is the most bananas you can get? Your puzzle answer was 2,242. So let's take a look at what I wrote. And there wasn't too much thinking about this here. I went with a fairly brute force solution. And my choice was essentially to, for each sequence of 2,000 numbers, track the changes. And if the list of 4 changes occurs, then calculate the diff, or rather calculate the price that corresponds to and insert it into a hash map. Now, of course, we only want the first occurrence that sequence occurs, so the hash map should have a key of the sequence of 4 numbers, and the result of the the first time that sequence occurs. Not the highest, it has to be the first time that sequence occurs. So essentially, that's what make_diff_stick is. It uses a linked list because I wanted something that would be easy to push onto the back of and pop from the front of. It needed to keep a track of the latest 4 changes going across the data set. So instead of having a vector where removing from the front means you almost have to reallocate the vector in many cases, I went with a linked list. Then I have diffs as a hash map. What the hash map is returning is diff key versus I32. And a diff key I did briefly show, it's 4 integers in a tuple. So it's literally brackets around 4 tuples, 4 numbers. So we can take the last, which is the ones digit of the secret from the initial number. We can make our secret mutable by doing let mute secret equals secret. And then you do for blank in 0 to 2000. So we're just doing 2000 iterations again. We calculate the next secret, we calculate its ones digit, and then we calculate the diff as the current digit minus the last one. Now remember, we can't use, there's no diff from the initial secret to the first one calculated, which is why it's safe to just leave this and not calculate a diff at this point. So we do a diff as digit minus last. Then we push it onto the back of the list. Now we check if the list is of length 4, then a sequence of 4 differences has occurred, and we need to figure out what the result is and store it in our dictionary. So essentially what we do is we iterate over the list, we store it in a tuple instead of a list. If there's a helper function to convert a list to a tuple, I don't know it. So this is what I'm using. And then we check if that entry exists for that series of 4 integers. If it doesn't, then we insert it. So this entry or insert will only insert something if there's nothing there already. Otherwise, we could have just done a diffs.insert. Right? If we had done this insert, it would have overwritten the number every time that sequence occurred. But because we only want the first time it happens, we use the entry or insert instead. Finally, we pop the front of the list because we don't want to store that for next time. And we want to keep the list at 3 elements so that when the 4th adds, it pushes into the dictionary and pops the front again. Finally, the last step of this loop is that we store the last digit that we calculated so that next time we actually get the diff of digit minus last. And that's it. Then we return the diffs dictionary. Now, one thing that I did wrong in this function when I initially wrote it was that I had misunderstood the problem, probably from not reading it properly, definitely from not reading it properly, where I thought that 0 didn't count as a diff. I thought it had to be a non-zero diff. So I wrote this that if there was a 0 in the list, then don't push it on, just pop from the front again. And that gave me the wrong answer. And for a while, it took me a while to realize why, until I went back and read the problem more thoroughly. And I realized that even one of the examples here contains a 0. So 0 is definitely a valid diff to use in your list. So from there, once I've got my diffs dict, I can do part B. Again, I parse the secrets out in exactly the same way. So I am doing this step twice, once for part A and once for part B. Then I'm calculating all the diffs by iterating over the secret, and for each one creating a diffs dictionary, and for each of those diffs dictionary, I'm inserting it into the all diffs dictionary. So what this step is doing is it says, look up the entry for the key. If it doesn't exist, insert 0, and then add on the value from the dictionary. So the idea is that if, let's say my tuple is -1 0 -1 0, right? So my first secret, starting from 1 gives a value of 8 after that, and my secret of 2 has a value of 0, or just doesn't have an entry in the hash map, right? Empty. Secret 3 is 4, let's say. So for each one, this make diffs dict gives me that secret 1 has this maps to 8. That's in the hash map, and that's what I'm looking up. Then I am checking, or rather I'm iterating over that dictionary and inserting all of the entries from the diffs dictionary into the all diffs. So that means that my all diffs will start out with, there's no entry for the key, -1 0 -1 0, so I'm going to insert 0. So in all diffs, this key maps to 0. And then there'll be other keys as well which map to other numbers. plus equals val. So for secret 1, that value is 8, so I'm going to add 8 on. For secret 2, if its diffs dictionary doesn't have an entry for this one, so it doesn't change this number. But it might have an entry for this one, let's say, so it might add on here, for example. And then the last secret in the list, it does have an entry for this, so it looks it up and it says add the value to it. So because we get 4 bananas from secret 3, we're going to add on here. So that means that my all diffs after this process, this hash map here, contains a list of diff keys for integers in a sequence and the number of bananas that I would get if I use that sequence. From there, it's a pretty simple operation to take the values, find the maximum one, and return that value. And that's part B. And you can see when I cargo run this, it does take a few seconds for it to run. 3, 4, 5, 6. So a little while, maybe up to 10 seconds. But after a while, it does complete, and that's because I'm going over the entire space and searching for the best. If I run this in release mode, it does speed it up fairly significantly. There you go, it takes about 1 second, so roughly a 10 times speed up without timing, just from guessing. And because I ran it in release mode, I felt that probably a second or less is perfectly fine. So I called that done on day 22, finished this puzzle successfully. So with that, thank you for watching, and I'll see you tomorrow for day 23.